While melting ice is a simple change in physical state, a chemical change involves a permanent alteration of composition. The original material is destroyed to build something entirely new. We identify these events through macroscopic indicators: abrupt color shifts, the sudden evolution of gas bubbles, or spontaneous changes in temperature. These visual shifts are surface-level indicators of a deeper mechanical process. At the atomic level, the structure is being entirely reconfigured. This process is governed by the law of conservation of mass. It states that matter cannot be created or destroyed within an isolated system. Every reaction represents a predictable, strictly accountable stoichiometric rearrangement of atoms. We define the anatomy of a reaction by its timeline. Reactants are the initial input materials, while products are the final output. Because mass is conserved, the exact number of atoms for each element must match on both sides of a chemical equation.
This chart shows iron and water forming iron oxide and hydrogen gas. The atoms are uneven, tipping the scale toward the products. We reach equilibrium by adding coefficients, 3 before iron and 4 before water and hydrogen, perfectly balancing the atomic count. These coefficients represent precise molar quantities. A mole is a standard scientific unit, used to measure large amounts of very small entities, like atoms or molecules. Balancing an equation provides the mathematical proof that a specific reaction obeys the physical laws of the universe. Combination reactions represent the first archetype, the synthesis of simple reactants into a single complex product. When solid calcium oxide, or quicklime, binds with liquid water, the atoms reorganize into calcium hydroxide. This industrial facility uses massive silos to process materials like quicklime. This specific combination reaction is a core component in the global manufacturing of cement. As these atoms lock together into new bonds, the resulting system holds surplus energy that is no longer needed to maintain the atomic structure. We define this as an exothermic reaction. The system expels its surplus energy into the surrounding environment as heat. Elements naturally seek these synthesized configurations because they represent a more stable, lower energy state. Decomposition reactions are the inverse of combination. Here, a single reactant fractures into multiple independent products. This fracturing requires a payment of energy. Decomposition is strictly endothermic, meaning it requires a continuous external energy source to break existing atomic bonds. In thermal decomposition, we apply intense heat to ferrous sulfate crystals. The heat forces the crystals to release sulfur gases and alters their color as they break down into iron oxide. Electrolytic decomposition, or electrolysis, uses electrical currents to pay the energy tax. This process tears liquid water molecules apart into their constituent gases. The results of electrolysis are mathematically fixed. As this chart shows, the process will always yield a precise 2-to-1 volume ratio of hydrogen gas to oxygen gas. Molecular bonds can also be fractured by light through photolytic decomposition. Silver chloride is highly sensitive to sunlight. Exposure to photons provides the kinetic energy necessary to break the compound into solid silver and chlorine gas. These vintage cameras and portraits demonstrate the historical application of photolysis. Early photography relied on the decomposition of silver compounds reacting to light, capturing images. Because chemical bonds store energy, tearing them apart always demands a precise thermodynamic payment in the form of heat, light, or electricity. In single displacement reactions, a highly active element forcefully hijacks a compound, evicting a weaker element. These takeovers are governed by the reactivity series. As shown, iron occupies a superior position above copper. When an iron nail is placed in blue copper sulfate, the iron displaces the copper. The liquid turns green, while a brown copper crust deposits onto the nail. Iron is thermodynamically driven to take the place of copper because of its higher reactivity tier. If roles were reversed and copper was placed into an iron solution, no reaction would occur. Displacement reactions demonstrate that a strict elemental hierarchy determines the outcome of these interactions. The final archetype is double displacement. This involves a mutual exchange of ions between two aqueous compounds. Aqueous refers to a solution where a substance is dissolved in water. When lead nitrate and potassium iodide are separate, both appear as clear, indistinguishable liquids. Once they are mixed, the ions instantly swap. This rapid reconfiguration causes the sudden manifestation of a vivid yellow solid. We define this insoluble solid as a precipitate. Its formation is the hallmark of a double displacement ion exchange. These four archetypes, combination, decomposition, displacement, and double displacement, account for the primary ways matter is reconfigured. Every molecular fracturing or fusion is bound by the stoichiometric accounting of mass conservation. These patterns lead into the study of redox reactions. Redox, shorthand for reduction-oxidation, is a conceptual layer where we track the transfer of electrons between atoms. Rigorous mathematical tracking reveals the laws of mass conservation through every colorful change. Master these patterns to understand how matter is reassembled across the universe.